In the last video, I showed you how to set up a simple RC circuit and derived equations for charging. In this video, I'll show you how to derive the equations for discharging. Let me remind you that the circuit looks like this during charging. Closing the switch completes the circuit, and the source of EMF drives the current around the loop. Charge builds up on the capacitor as the current flows. In this particular setup, positive charge accumulates on the top plate and negative charge accumulates on the bottom plate. To discharge the capacitor, the source of EMF is removed and the capacitor and resistor are reconnected to reform the circuit. The current will now flow in the opposite direction through the resistor as the capacitor is discharged. The goal of this video is to derive the equations for discharging in the RC circuit, and to do that I'm going to use Kirchhoff's loop rule as I did in the last video, but this time my loop is going to look like this. Starting with the capacitor and going around the loop, Q over C minus IR is equal to 0. Now the current in the circuit is dQ by dt, but the charge on the capacitor decreases as the current flows. This means that dQ by dt for the capacitor is minus I, and this is the substitution I'll make into the equation. This is one of the subtlest bits of this derivation, so think hard about it and also think about why it's okay to leave I as dQ by dt in the derivation of the charging RC circuit. Making the substitution for current, I am left with Q over C plus dQ by dt times R is equal to 0. And this is a separable differential equation. That's the physics, and from here I'm going to use calculus to solve this equation for charge on the capacitor and current in the circuit as a function of time. Rearranging a bit, I have Q over C equals minus dQ by dt times R. I'll multiply through by C to clear it out of the denominator, and then I'll put minus dt over RC over on the left and collect dQ over Q on the right. The variables are separated, and I'll add some integrals, remembering that I also need to include the constant term. Integrating yields minus T over RC is equal to ln of Q plus a constant. Now to find the constant term. At t equals 0, the capacitor has some initial charge, and I'm going to call that Q naught. Making these substitutions into the equation with the red star gives me 0 is equal to ln of Q naught plus a constant. And rearranging, I have constant is equal to minus ln of Q naught. Now I'm going to make that substitution back into the equation with the red star and get minus T over RC is equal to ln of Q over Q naught. Now I can exponentiate both sides. E to the minus T over RC is equal to Q over Q naught. And finally, rearranging, I find Q is equal to Q naught times E to the minus T over RC. And I'll put a box around that one. Now remember that current is equal to minus dQ by dt, so I is equal to Q naught over RC times E to the minus T over RC. And I'll box that one as well. It's worth plotting Q and I for discharging as we did for charging in the last video. The charge on the capacitor starts at some initial charge, Q naught, and decays to 0 over time. Meanwhile, the current starts at Q naught over RC and decays to 0 over time. Let's see what happens to charge and current after one time constant. So at T is equal to tau is equal to RC, we have Q is equal to Q naught times E to the minus RC over RC, which is equal to Q naught times E to the minus 1, which is 0.37 times Q naught. Meanwhile, I is equal to Q naught over RC times E to the minus RC over RC, which is 0.37 Q naught over RC. Now remember that Q naught over RC is the initial current, so that's also equal to 0.37 times the initial current. In other words, both current and charge are at 37% of the initial value after one time constant. So these are the equations for discharging the simple RC circuit. And of course, we derived the equations for charging in the last video. These are equations that you want to have readily available, but I want to add in a word of caution. These equations are so appealing that it can be tempting to overuse them. Don't fall into that trap and think twice before using the equations in the context of more complicated circuits. For example, in this RC circuit, two capacitors have been arranged in series. In this case, you can find the equivalent capacitance of the circuit and just replace all of the C's in the equations with the equivalent capacitance. But here's another example where a resistor has been placed in parallel with one of the capacitors. It isn't so obvious how to fix up a circuit like this one. We can still say some things about a circuit like this, and if you want to learn more about that, you should check out the next video, but you shouldn't just try to force these equations to apply. As long as it's a simple RC circuit, the equations are quite useful. Get comfortable with them, and it's also worthwhile to go ahead and learn the derivations so you can reproduce them from scratch. When you're ready for a more complicated RC circuit, check out the next video.